Bismillahirrahmanirrahim. Dear students, welcome to the Electrical Engineering channel. In this lecture series, I am going to start a new course, and the name of that course is Linear Algebra. And in this course, I will be discussing system of linear equations, vector spaces, linear independence, basis, and dimension. Then I will discuss rank of a matrix, determinant, and inverse. Then eigenvalues and eigenvectors will be discussed in detail. And finally, the last content of this course is a system of linear differential equations. And for this course, the recommended books are as follows. The first book is Linear Algebra and its Applications by David C. Lay. And the second recommended book is Linear Algebra and its Applications by Gilbert Strang. So the definition of linear algebra is a branch of mathematics that is concerned with mathematical structures closed under the operations of addition and scalar multiplication, and that includes the theory of systems of linear equations, matrices, determinants, vector spaces, and linear transformations. So, all of these principles and rules and theorems of mathematics are actually part of linear algebra. The first topic of this course is solving linear equations, and before starting this topic in terms of linear algebra and its rules and its theorems, I will be solving these equations by conventional methods which we already have studied in our previous classes. So, for example, we are given two linear equations or simultaneous equations. The first equation is x plus 2y is equal to 3. Second equation is 4x plus 5y is equal to 6. So these are called simultaneous equations, and it is a set of linear equations. And the principle of solving such equations is that we have equal number of unknown variables and total number of equations. So if we have two equations, there will be two unknowns. And if we have two unknowns and we have one equation, then we cannot solve such equations. Similarly, if we have five unknowns, but we have four equations, again, we will not be able to solve that set of linear equations. So the number of unknowns must be equal to the total number of linear equations. So in conventional method, such a set of equations can be solved by eliminating one variable first. So this is done actually by multiplying the first equation by 4. So the first term will become 4x in both the equations, and then we can subtract one equation from the other, and one variable will be eliminated. So the other variable can be evaluated. Okay, so the first equation will become 4x plus um, the second equation is 4x plus 5y is equal to 6, and first equation will become 4x plus 8y is equal to 12. So subtract the new equation from the second equation. This 4x will be cancelled out, and at the end we will get minus 3y equal to minus 6. So y will be equal to 2. So we can back substitute this value of y in either equation 1 or equation 2, and we can get the answer of x, right? So put y is equal to 2 in equation 1 or equation 2. So it will become x plus 2y equal to 3. So y is equal to 2. So x plus 4 is equal to 3. So x will be minus 1. Similarly, we can substitute this value in the second equation, and second equation is 4x plus 5y equal to 6. And upon solving this equation, again we will get x equal to minus 1. So this is one way of solving simultaneous equations. Second method is also very simple, and that is called Cramer's rule, and it will solve the simultaneous equations in matrix form. So we can write this set of simultaneous equations in matrix form. So the coefficients of x and y can be written in the matrix form, and x and y can be written in the column form. And this 3 and 6 will also be written in the column form. So 1, 2, 4, 5 x, y is equal to 3, 6. So this 1, 2, 4, 5 is called the system equation, right? And we can evaluate the value of x by replacing this first column by this column 3 6, right? So 1 4 will be replaced by 3 6, and 2 5 is the second column, and we will take the determinant, and that determinant will be kept in the numerator, and in the denominator the determinant of the system matrix will be placed. And by evaluating these two determinants and taking their ratio will give us the value of x. So x is equal to -1, and this is the same answer which we obtained in the previous method. Similarly, the value of y can be evaluated by replacing the second column of the system matrix with this 3, 6. So it will become 1, 4, and 3, 6, right? 1, 4, 3, 6. And in the denominator, we will again have the determinant of the system matrix. And by evaluating these determinants and taking their ratio, the value of y is evaluated to be 2. So this is the same answer which we obtained in the previous method. So this is another way of solving simultaneous equations. So mathematically, these equations can be solved by these methods, and but graphically, there should be some physical interpretation behind the solution of these simultaneous equations. So both these equations actually correspond to lines, straight lines. Okay, so this is equation of a straight line. This is also the equation of a straight line. So since these are linear equations, so they will correspond to straight lines. And if there is any variable whose power is 2, for example, x square or y square, then that equation will become second order equation. So that will not be a linear equation. So the linear equation will have maximum power of each variable as 1. So this is one straight line, x plus 2y is equal to 3, and this is second straight line, 4x plus 5y is equal to 6. And the solution of these two equations will correspond to the point of intersection of these two lines. So this is the point of intersection, and it is actually -1, 2, x equal to -1 and y is equal to 2. So this point is actually the solution of these two equations. So in some cases, we are given two equations, but the solution of those two equations is not defined, right? For example, if we have one equation x plus 2y is equal to 3, and second equation is 4x plus 8y is equal to 6, and if we try to solve this set of equations, they are written over here: x plus 2y is equal to 3, 4x plus 8y is equal to 6. So let's eliminate x. So after eliminating x, we have to multiply the first equation by 4, so it will become 4x plus 8y is equal to 12. When we subtract that new equation from the second equation, we will get 0 at the left hand side. So x will be eliminated, but at the same time y will also be eliminated. And at the right hand side, we will get -6. So 0 is equal to -6. So we cannot evaluate the value of either x or y by this method. So it means the solution of these two equations is not defined, and graphically these two equations will correspond to parallel straight lines. So this is one equation, x plus 2y equal to 3. This is second straight line, 4x plus 8y is equal to 6, and they will never intersect with each other graphically. So the solution of these two equations doesn't exist. Similarly, another case is that if we have such a set of equations, x plus 2y is equal to 3, 4x plus 8y is equal to 12. If we try to solve these two equations, again we have to eliminate one variable, which is x. So let's multiply first equation by 4, and first equation will become 4x plus 8y is equal to 12. Second equation is also same, and if we subtract any of the equation from the other, we will get 0 equal to 0. So none of the variable can be evaluated by this method. So it means both these equations are actually same. So if we multiply first equation by 4, it will be exactly equal to the second equation. So it means both equations are same, and if we plot both equations, they will correspond to the single straight line. So one straight line will be lying at top of the other straight line, and in this case we have whole line of solutions because there will be infinite points which are intersecting with each other. So there are infinite intersection points or common points in these two equations, and in this case the whole line of solution will be evaluated. So this type of uh, system of equation is also non-solvable, and we can say that the solution of these two equations doesn't exist. So if either we have such a case or if we have this case of parallel lines, we will say that this is a singular case, because if we make uh, matrices from these two equations, and if we take the determinant of that matrix, that will be equal to 0, right? So that matrix is called a singular matrix, and in this context, we will say that these two equations constitute a singular case. So whenever we have a singular case, or whenever there is a singularity, the solution of that set of equations is not defined or it is not possible. So let's move to another discussion, and that is the representation of simultaneous equations in column form. So this is one equation, this is the second equation, and these two equations can be represented in the column form. We can take x common, and 2, 1 can be written in the vector form or column form. Similarly, plus y is taken as common, and minus 1, 1 will be written in the column form, and in the right hand side we will have 1, 5 also in the column form. So similarly, this column form can also be written for three variable case, and in that case we will have u here. 2 minus 4 2 will be in the first column, plus v into 1 minus 6 7. So this is minus 6v. For u minus 6v, by mistake it is written as plus, but in fact it is minus. So 1 minus 6 and 7 plus w into 102, and that will be equal to 5 minus 2 9, right? So this is our column vector which is represented by b, and from here we can estimate the values of u, v, and w, right, by closely inspecting these column vectors. Okay, so if I add this first column and second column, and I multiply the third column with 3 and add in the sum of first and second columns, I will get the right hand side, right? Because this is 2 plus 1 plus 2 will be equal to 5. 4 minus 6 plus 0 is equal to minus 2. Minus 2, 7 plus 4 is equal to 9. So if I multiply this column by 2, and if I add these three, all these three columns, then I will get this answer, right? So this is what we have observed by looking at the three columns, and this can be written as 1, 1, and 2. So it means this value is equal to 1, this value of v is equal to 1, and this value of w is equal to 2. So this method will give us the solution of these three equations without solving it either in the variable elimination method or by the matrix method. So this is one way of solving simultaneous equations, but this is not all the time so simple as we have done now, right? Every time it will not be possible to get the solution by this trivial method. So uh, this method will give us a way to validate our results or validate our solution. But if these column forms are simple, we can estimate the result by just looking closely at the three equations, right? So this is one way of solving simultaneous equations. So in three variable case, when we have three variables, there will be three equations, and in three variable case, uh, we can also define the case of singularity, right? So when we have three equations, there will be actually three planes, and the single common point of intersection of all the three planes will give us the solution. But not all the time, all the three planes are intersecting at one common point, and that case is called singular case. And if we have such singularity, the definite or concrete solution of those set of three equations will not be possible. So, for example, this is a singular case. We have one straight line, and these two straight uh, planes are actually parallel with each other, and the solution is not defined in this case. Here we have three planes, and all these three planes again are not intersecting at single common point. Here we have three planes, and all of these three planes are parallel with each other. So the solution in this case is also uh, non-existent. Okay. So for example, if we have a set of three equations, and these all these three equations will correspond to three planes, three different planes. And let's try to solve this set of equations. And 1 plus 2 is equal to 3, right? In the left hand side, but not true on the right hand side. That is 2 plus 5 is not equal to 6. So if we add first row in the second row, we will get the third row at the left hand side, because 1 plus 2 is equal to 3, 1 plus 0 is equal to 1, and 1 plus 3 is equal to 4. but this is not true for the right hand side. So 2 plus 5 is equal to 7, but here we have 6. So again, this is a singular case, right? And the solution of these three equations doesn't exist. Now, even if we replace this 6 by 7, again, you can see that 1 plus 2 is equal to 3 for left hand side as well as the right hand side. So in this case, at the end, we will have such scenario 0 equal to 0. And when we have 0 equal to 0, it means we have too many solutions. So again, the solution of these three equations doesn't exist. And the solution of these three equations doesn't exist as well. And both of these cases are actually singular cases, right? So if you take the determinant of the system matrix corresponding to these three equations, the determinant will be equal to 0. So these two cases also correspond to singularity, and we don't have any specific solution. Okay. So in this case, we have three planes which have a line in common. Okay. So here we have again too many solutions. So only definite solution exists when all the three planes intersect at the single common point, which I have shown in this figure. So there are three planes and all of them are intersecting at one common point. So in that case, this definite solution exists. So that is all about our today's lecture on the introduction of linear algebra and simultaneous equations. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.